We're Team 20, and this is our final presentation. The device we picked is the Hoken Newtonian Reflector Telescope. We estimate this product to be sold at 50,000 units per year.
Going over our target customers, our primary customers are recreational users who are amateur astronomers who might use the telescopes for casual stargazing, photography, and amateur research projects. Our secondary customers are schools, colleges, and universities who might use the telescopes for student learning. Here's our parts list and the number of parts, as well as which subassembly they correspond to. We have 23 parts. Here's an image of our CAD along with the corresponding part numbers.
Here we see the FAST diagram. This diagram will show how our product will achieve its main function of magnifying objects. It'll achieve this by moving the viewpoint and resisting motion. We have shifted one of our functions to be providing overall support.
Moving on to the function component mapping matrix, it was a tool we used to visually display how each component contributes to key functions, and this aided in our part selection for redesigning for assembly and manufacturing purposes. Next is the quad chart, which helps us to organize primary components based on the manufacturing cost and functional importance, and this was also used in our part selection process.
We then compared the functionalities of the different consumer groups. The functionalities that differ between the consumer groups were portability, adjust focus, and adjust height. Based on these functionalities that were found to vary, the parts that differ between groups were the body and the tripod. For the body, the main difference comes from the eyepiece and focus knob. A more advanced inner working allows for different optical outcomes. Similarly, the tripods are similar in design nature, but their height range and structure, as well as materials, are dependent on their use. Here's a visual of the common interfaces with module components. On the left is the telescope body on a common mount, and on the right are the tripods on each base.
This is the unmodified product family assembly diagram, where the variation is dependent on the primary and secondary customers. It's all based on the winning fishbone assembly sequence. The numbers represent the variety of branches, and then the different color for telescope tube means that part is varied. The modified sequence is the opposite order of assembly in order to allow for delayed differentiation.
To aid in the part selection process for manual assembly, we found the total assembly time of every part of the telescope. Overall, most parts had a small assembly time that lasted under 7 seconds, but there were some heavy outliers. We observed many repeating parts take up a large amount of assembly time, but individually didn't cause too much of an issue. We decided to focus on parts we believe would have a significant drop in assembly time through redesign. From the quad chart classification, we chose the telescope platform part and the tripod plate module part to redesign for. This was chosen because of the high importance of the product. We saw the opportunity in both parts for simplification that would reduce the overall cost and reduce the assembly time. This is especially important in the tripod plate, which has the largest assembly time of all parts. We see from the function component mapping matrix that the primary function of the telescope clamps is to secure position of the product. The tripod plate has a variety of functions. It secures the legs to prevent any shifting within the base and keeps the telescope planted firmly in its location.
This is the CAD of the tripod plate before and then after design for manual assembly. There are 4 DFAs applied. First is DFA 1, which is reduced part counts. The top and the bottom of the clamp sticks would reduce from 6 parts to 3 parts with these changes. The second is DFA 10, which is add features for easy insertion. There's a chamfer added in the center hole in order for mount A to be more easily inserted. DFA 11 is provide locating features. The 3 holes on the outside have bosses added to allow for easier alignment of the top of the clamp sticks. And finally is DFA 3, which is prefer snap fits, and this would cause for a redesign of mount A, which would need to be redesigned for a snap fit. There's no change to the part function, but there is a huge decrease in the assembly time from 57 seconds to 21.5 seconds, and as well as reduced manufacturing costs due to less material.
This is the CAD for the telescope clamps before modification, where both clamps would be screw tightened around the telescope tube, and they would both fit into a slot on the mount that is secured with a screw, and this led to an assembly time of 19.9 seconds. Moving on to the clamps after modification, we combined the 2 clamps into just 1 clamp, which reduced the part count and reduced the fasteners. We also added ridges that would enable a snap fit onto the mount. The mount would be updated accordingly. And lastly, we removed the mounting feature on top of the ring to only have 1 on the bottom, therefore making it easier to orient. This would have no change in the part function. There would be a reduced assembly time of 16.1 seconds, so now only 3.8 seconds. and the manufacturing costs will be reduced due to the decreased number of parts and the removed extruded feature on top.
From the quad chart, we chose the platform subassembly of mounts A through D to redesign for. This includes the through shafts within the mount parts. This was chosen because of the high importance of the subassembly, but corresponding high cost. We see from the mapping matrix that the primary function of the mount subassembly is to allow for a variety of degrees of motion within the telescope.
For design for automated assembly, we chose the mount subassembly. We know that this subassembly would technically be too large to perform this operation, although it was the only subassembly within our telescope that we could feasibly perform this on. We estimated the handling and insertion costs to be 15.44 cents. So next, we identify these 3 DFAs that allowed us to make the corresponding changes, which include reducing the part variety, so making both of those through shafts the same part, increasing symmetry, so reducing some of the unnecessary circular features that were on the through shafts, and also add features for easy insertion of our shaft to go into the telescope mount. And this led to a reduced assembly cost of $13.56, leading to a simplified design without reduction in part function.
The first part that we looked at for design for manufacturing is the mount through shaft, which is part of the mount subassembly and main functions to allow for rotation. The material used for this part is aluminum, and based on this, as well as the other attributes of the part, we narrowed down the processes to investment casting, machining, or additive manufacturing. Based on the characteristics of our part, we selected machining as our final process.
Here's the manufacturing plan before of our mount subassembly. And here's the DfM Pro analysis that we performed to estimate the total cost per part. This allowed us to discover key areas that we could improve our DfM on this part. We also performed Hubs analysis. This is a sample, just a sample of the analysis that we did, and we took different quantities and used those to extrapolate to get the Hubs cost per part that is seen on the next slide. So here's our design for manufacturing after. As you can see, we implement changes from 3 DFMs as identified by our DfM Pro. We'd also like to note that there are still room for improvement to make this part better, although we believe that by showing our % reduction in both our analytical and Hubs part cost estimation, that this analysis was successful. And here is the after of our mount subassembly manufacturing drawing.
The second part we selected for design for manufacturing is the tripod plate. While it serves many functions, the main function we focused on was securing the position of the telescope. The material used for this part is the polymer ABS. Based on this and the other characteristics of the part, we narrowed down the processes to machining, injection molding, blow molding, and additive manufacturing, but selected injection molding as our final process.
Here's the CAD manufacturing drawing showing the critical dimensions of the tripod plate before DfM. The injection molding tolerance is plus or minus 0.35 millimeters. And just wanted to note that the dimensions of the holes are the most important dimensions as they deal with fastening and smooth operation of the tripod. So again, looking at the tripod plate before performing DfM, we figured out that the total cost would come out to $5.28 per part, and DfM Pro shows us some areas for improvement. After applying DfM, we were able to get a 27% cost decrease, leading the total cost to be $3.87. We were able to knock out some of the errors in DfM Pro by applying guidelines such as keep uniform wall thickness, adding draft angles, and avoiding sharp corners. This had no effect on product function as well as on the assembly costs. And this is the critical dimensions after performing DfM. There is no change in the critical dimensions.
The suggested product service system is maintenance and repair service. This would improve customer service through convenience, quality assurance, and extended product lifespan, and it would reduce the negative impact on the environment in terms of product lifetime, resource efficiency, and refurbishing parts. Without this service, customers face higher costs, and the telescopes could be discarded more prematurely, leading to environmental degradation.
To conclude, our redesigns of both manual and automated assembly parts show a significant decrease in cost per part and total assembly times, with $1 taken off multiple parts and a reduced overall assembly time of 51.6 seconds. We consider our redesigns a success that would make this product easier and cheaper to manufacture. If given the opportunity to start again, we would like to work more on simplifying the legs of the tripod as we discuss multiple opportunities to simplify and reduce the part numbers. We are overall happy with the final product we created and are happy to see the effect of just a few careful designs and what their effect is overall.